All right, so the lab we're going to be working on here, guys, is going to test the relationship in this formula. Okay, the force of friction is mu times the normal force formula. Okay, that's the relationship that we're trying to test. To that end, we are going to use an inclined plane to do that. Right? Now, the best way to do that with the inclined plane is to actually use the flat side, not the side with the grooves in it. Okay, because if you put the box on here and the box isn't centered on these grooves, it might tip into the grooves a little bit and change things for us. So we want to be as controlled as possible by using the flat side. Okay, so the way this is going to work is you're going to have a box of masses. Okay, on the bottom of the box of masses is this like sticky stuff that we've put on the bottom of all of them. Okay, it increases the coefficient of friction between the box and the ramp, but it will stay the same throughout the entire experiment. Okay, what we're going to do is change how much mass is in the cart, but that's not necessarily what we're manipulating. When we change that, it changes something else in this formula. Okay? Because really what we're testing in this formula is the relationship between normal force and the force of friction. Okay? So one of these is our manipulated and the other is our responding. Okay, everyone follow me there? Okay, so we're going to be measuring some other things, but those are the two main ones. There's probably more than one responding variable in this lab, but the most important one is the one that we're going to, is one of those two. Okay, and obviously the other one is the manipulated, so you have to figure out which one's which. Okay, so the way this lab is going to work is we are going to start with no masses in the box. Okay, so all the masses are going to be out of the box, and all that will be in there is the plastic case that the masses go in. All right, and you're going to put that on the ramp. Okay, on the spot where it makes good contact with the ramp. There's no screw holes or anything. Put it on a nice flat part of the ramp. Right? And what we're going to do is you're going to take your phone and you're going to put it on the clinometer. Okay? The clinometer is in your utilities. Okay? It's in with the same thing as measure. Okay, so your measure app, if you have an iPhone, I don't know how it works on an Android phone because I don't have one. Okay, but you just hit measure, okay, and you can put the level on there. Okay, there's a level option. And it tells you the angle your phone is at. Okay, everyone with me so far? Okay, so if I put this on the ramp, it's level. What I'm going to do is lift the ramp until the box just starts to slide. And then I'm going to hold it there and get the angle. Everybody with me? So the only thing I'm actually measuring here is the mass I have in here and the angle the ramp gets to before it starts to slide. Okay, I'm going to use those numbers to get those two things. Okay, everyone with me? Okay, so this is like a pretty straightforward lab to do, right? But notice when I got this thing going, how slowly I lifted the ramp. Okay, like I didn't just go, oh, there it goes. Okay, I lifted it very, very slowly. It's important that you do that. If you just lift it quickly, you're kind of making this a catapult and almost trying to throw the box right off of the ramp. So make sure that you lift that very, very slowly until it starts moving. You probably want to have one person lifting and one person watching the angle on the phone. Okay, and then as soon as you see it start to move, do your best to stop right there so that they can get an accurate read on the angle. Okay, so by doing that, what we're really doing is finding what the maximum static frictional force is for that particular normal force. Okay, everyone with me? Right? So when there's no mass in here, this thing has a mass of 0.178 kilograms. Okay? I'm finding what the maximum amount of static frictional force is for that normal force. Okay? Now, on an inclined plane, how do I calculate normal force? Quick reminder here. On an inclined plane, we have this internal triangle, right? Okay, so we're always going to be dealing with this side of the triangle. Okay, that's going to tell us the normal force. If we're just getting it to move, we're essentially saying that the net force is just slightly off of 0, and that F parallel will be equal to what force at that point? If it's just starting to move, the force down the ramp and the force up the ramp are equal. Okay, so I'm using F parallel as a measure of my frictional force. Okay, and I'm using F normal, okay, to go with that. Okay, to kind of compare the two. Okay? Questions so far? All right. I did a really, I can't think of the word I'm looking for. I didn't really give you many of the variables outright there, but they're all included in what I just said. Okay? We're recording angles, we're recording normal force, we're getting friction indirectly through force parallel. Okay? We're going to use, we're going to have this ramp. Okay? We're using this side of the ramp, same box. Okay? All those kinds of things are going to be important. Okay? All right. So, for our hypothesis, okay, the if part of our hypothesis should talk about the relationship between normal force and force of friction. Okay? Is it exponential, inverse, linear, polynomial? You tell me what you think the relationship is there. That's what the if part of your hypothesis should talk about. Okay? The and part, as always, describes the experiment. Okay? On an inclined plane, various normal forces are compared to the force of static friction. Okay? And then how would you calculate mu from a graph of normal force versus friction? Okay? Now, in any graph, which variable goes on the x-axis? Manipulated, responding, which one? Which variable always goes on the x-axis of a graph? Manipulated or responding? Manipulated. Okay? Your manipulated variable always goes on the x-axis. That way you can see the effect on the responding, which would be on the y then, okay, of increasing your manipulated variable. That's why we do it that way. Okay? So think about that when you're building your graph of normal force versus friction. Which one of those forces has to go on the x and which one has to go on the y? Okay? And we want to use that graph to calculate mu. Okay? There should be a way to get it from that graph. Okay? Questions so far? All right, so that's your hypothesis. Okay? For the procedure here, okay, we've kind of vaguely outlined it here. So you're going to set up that apparatus, lay the track flat, okay, slowly raise the ramp until the box begins to slide, and record the angle at which it begins to slide. Okay? And do that for different masses, okay, in the cart or in the sled. Okay, calculate the normal force for each trial using Fn equals Fg times the cos of theta, right? So you can always calculate Fg, mass times gravity, 9.81. Okay, so 0.178 plus whatever you put in there. Okay? And then calculate F parallel using Fg times the sine of theta. That's how we always calculate it. This will be your maximum force of static friction. So whenever you calculate F parallel, that is your force of friction for that trial, because we're saying this is where they are equal and where they are at their maximum. Okay? Everyone all right with that? All right, then you're going to plot that graph, okay, and determine the coefficient of friction between the block and not the floor, the block and the ramp. Okay? So in your report, you've got a couple of different charts. Okay, so if we're looking here, okay, you've got this first chart, okay, where you're going to put the mass, whatever it happens to be, and record the angle. Mass, record the angle. Then you're going to do this second chart, okay, where you're going to fill in the masses will be the same. Calculate the normal force, Fg times the cos of theta. Calculate the static friction, mg sine of theta, and those are the two things you're going to graph, okay, is those two columns. So you can just highlight that, copy them right into Google Sheets, okay, and graph it. Okay, everyone with me so far? All right, now the one thing you need to make sure of, I've already put the units up top here. Don't put units in the boxes. Because if you do, when you copy ends over into Google Sheets will have a conniption fit. Because it doesn't know how to graph letters. And if you have letters in the box with numbers, it gets very confused. Okay? All right, for the, let's just do the procedure part. So we've got 6 different trials that we're going to be doing. Now, we have to make sure that the changes between trials are significant enough that we get a difference. So your first trial is the box empty. Don't make the second trial the box and this thing. Okay, this is not going to make enough of a difference for you to get good data. So I would say, since we're doing 6 of these, your first one is empty box. So for everybody, the first one would be 0.178 kilograms. Okay, and then for the second one, let's say we'll put in all the little ones. So 2, 3, 4, 5, 6. Okay, so you'll put in the 5 smallest ones for your second trial. Okay, the 5 smallest masses go in for the second trial. Okay, and then put in 1 more mass every trial after that, and you get to 6. Okay, you want to follow the procedure? Okay, let's get the procedure done, then we'll talk about what we've got to do with our data. All right, so everybody grab a box of masses and a ramp. The group can take this one if they want it. All right, so if your data did this, that's okay. Okay, if your data, like, you probably expected to get a regular trend with your angles, but you don't. Okay, I totally expected that the first time. Actually, it was both me and Mr. Dickey were doing this when we were designing this lab, and we were actually getting frustrated to the point where we were raising our voices with each other because, like, why is it? And then we went, oh yeah, right. And then suddenly dawned on us why the data would do this, and that we had, well, really not been very smart. And so it's totally cool if you look at this data and go, I did something wrong. You didn't do anything wrong. This is what it's supposed to do, and it's okay if it did that. I know it doesn't feel right, but it is. Okay, so if your angles kind of went all over the place, that's okay. All right? So if we're looking at what we're doing here in this lab, we are essentially saying that every time we do this trial, the force of friction acting up the ramp and the force parallel are equal. Because we did this for the instant it starts to slide. So we're kind of saying, all right, it was the instant it started to slide, but it's the instant right before that where the net force is still what? Still 0, right? Because once it starts to slide, we're dealing with kinetic friction, not static. So we're making a slight approximation here. Maybe that's a source of error. Okay, but that's what we're doing. We're saying that at that instant, these two forces are equal because the net force is 0. Okay? Now, we know that as we increase the mass of this block, this force changes. And so does this force, because this force changes when we increase the mass of the block. Okay? Now, these forces change not only in response to that mass, but also in response to the angle. And that's why the angle did weird things. We were changing essentially 2 things that could affect both normal force and F parallel. And that's okay. Right? That's just the way we'll be doing the lab. All right? So that's the setup that we're essentially using here. So when we get to these charts, okay, you're going to calculate your normal force. Okay, remember that that's going to be force of gravity times the cos of theta. Okay, for our static friction, that's going to be force of gravity times the sine of theta, right? And those are the 2 forces you're going to graph. Now, what should you expect your graph to look like when you graph those 2 forces? As you increase normal force, according to this formula, okay, in this lab, we were increasing this force, or changing this force, This was staying the same. So if I change this, what should happen to that? If I increase normal force, what should happen to FF? Think about when I pushed on the desk, right? When I lifted the desk and pulled it versus when I pushed on the desk. If I increase normal force, what happens to friction? It should go up, right? So what should our graph look like then? Right? It should show that. This doesn't have any exponents in it, does it? So there shouldn't be any curves or anything, right? Nothing squared or cubed in this formula. It says that if I was to double that force and this stays the same, this should double, right? That's the relationship they should have. Is everyone okay with that idea? Because that's what we're testing here. We want to see if that holds true. Okay, so next step is for you to build your graph. So make these calculations, put those numbers in, and then copy them into Google Sheets and build your graph. Okay? Once I see a few graphs built, we'll talk about the rest of the analysis. Okay, if we're looking at our data here, okay, so we're going to build a graph like this. Okay, we're going to have normal force and friction on there, and it's going to give us effectively that relationship. Okay, from this graph, we need to calculate mu. Okay, we have the other two parts of the formula on that graph. Okay, and we have what their levels are at several different points, one for each of our trials. Okay, Google Sheets is kind enough to show us the relationship between those two as a trend line. So, spoiler alert, you need to put a trend line on your graph. Okay, and probably the equation for it would be useful. And maybe something in there will represent mu. And by maybe, I mean it will. You just have to figure out what part of that would represent mu and give me a justification. Okay, that is what the analysis asks you to do. Okay, so the analysis is fill in this chart, build the graph, and then it says with your graph, okay, along with your calculation of coefficient of friction, justify/explain your calculation. So I'm going to want to see how you got mu, and then I want you to justify to me why that method gave you mu. Okay, so a couple of sentences at least, okay, explaining here's the relationship that was on the graph, here's why this calculation is going to get me mu, okay, and this is, kind of just give me some explanation in there.
So would we do all the trials, find mu for all of them and then average it?
No, you're getting it from the graph. So it's one calculation. Okay, get it from the graph. Okay, so did everyone catch that? What I don't want is for you to calculate mu for each trial. Okay, that we wouldn't need a graph. I wouldn't ask you to build a graph if that was the way I wanted you to do it because it's extra work. Okay, I want you to do the graph because the graph is the better way to do it. Okay, everyone with me there? All right, so get your graph built. You're going to find it still generally does this, even though your angles may have looked a little bit crazy. Okay, this is still the way it's going to go for you. Right, and then get that analysis part done. Okay, for your conclusion, guys, same as always, copy paste your hypothesis. Okay, was the relationship what you predicted? Were you able to calculate mu using the method you predicted? If not, what did you do instead? Accept, reject. Okay, and then sources of error. Think of a couple there, guys. Okay, I kind of mentioned one a little offhandedly while I was doing the explanation there, but there's more than probably 4 or 5 acceptable sources of error within that experiment that you could do nothing about, but were just inherent to the way we did it. All right? Here, I'll give you one thing that you can think about for a source of error. Did you put the sled in the same spot every time? Hopefully, or at least close. Yeah. Did you wipe that spot off on the bottom of the cart each time? Was there a reason you might have wanted to do that, looking back? Because it wasn't in the procedure. It didn't say in the procedure to do that. Okay? But there might have been a good reason for it being a good idea. But I don't put it in the procedure so that you can get a source of error. Because if I put it in there, it eliminates one of the sources of error you could pick from. Okay. All right. You still got the rest of class. That's still what, 20 minutes or so, so you should be able to get quite a bit of this done and not have too much homework.